something that he said to me made my jaw drop. He said, we're building nuclear reactors and we are on the edge of a cliff. And just recently have they started to implement security measures that concern malware attacks, that concern internet adjacent systems, taking into consideration those factors in the design cycle. So today, what I'm going to talk about is some vulnerabilities that Tenable found. In the last year or so, we found about a dozen critical vulnerabilities in different ICS and SCADA products, hardware and software. They're critical because they're pre-authentication, remote code execution on production software, production hardware. And so I'm going to talk not about all of them. I'll talk about 4 of them in detail, and then we'll go into an attack scenario, and we'll blow up a nuclear power plant. First one, in Siemens, huge manufacturer. Siemens makes a software product called Step 7. Step 7 is used industry-wide. It's been around forever. They rebranded it recently as TIA, Totally Integrated Automation Portal. And it's used in all aspects of ICS development and operation, from design phase to implementation, all the way down to operation. TIA Portal has a suite of simulation tools. It's got diagnostics and telemetry, which are used in operation and in production, as well as energy management for use in operation. And it's built by and for engineers. It's made for the integrators and all the way down to the people actually operating the technology at the plant level. So the first vuln, this vuln that we found, is in this software. It exists in the authentication package. TIA Portal has a server which is implemented by Node.js, and basically it implements functionality for authenticating web users and then swapping over to a WebSockets protocol. After authentication, when it's switched over to WebSockets, however, they don't use the token that's generated from the SSL authentication. So the result is that any attacker can just start sending WebSockets commands, skipping authentication. And of course, all administrator functionalities are included in the WebSockets protocol. So the result of that is that you can do a number of things, but the best thing to do is to just start a firmware update. And you can control and specify the firmware update server, so an attacker can use this to run basically any binary served from their own controlled server. Some other things that you can do with it is to modify user permissions or create a new user, modify existing user credentials, or you could just basically change application proxy settings to collect system information. And I would stress again, like this is an in-production software suite used all over the place. All right, number 2. So Schneider Electric, they make Indiesoft Web Studio. And earlier this year, we found a bunch of vulnerabilities in Indiesoft, but this one was kind of the most critical one, to where there's a vulnerability in the command processing functionality, where you can actually end up overflowing the stack. The command is called the command 66. It's this message which can be sent by an unauthenticated remote user, and it's used to specify a database configuration update server. So the file that's sent back by the database update server has the ability to set specific database configuration parameters. The problem exists, though, that the Indiesoft Web Studio executes the engine has this capability to parse user commands. So it takes these wrapped command and executes them on the operating system as the administrator. And this happens because the developers basically overlooked the engine's markup parsing. So as Indiesoft parses the malicious update configuration file, it executes those wrapped bracket commands in the administrator shell. And then we have a proof of concept of this on our Tenable GitHub repository, where a fake SMB server is created the database configuration is requested from the Indasoft server. It requests a malicious configuration file and then runs it. And we use that to just run calculator on the Indasoft Web Studio server. All right, a third vulnerability. This one is also in Schneider Electric, this time in hardware. So the Modicon Quantum is a family of PLCs, and they're produced by Schneider, and they're used all over across different industries. They're designed to be modular and interchanged in the housing, depending on the needs of the application. One of the vulns that we found, there were several of them, but one of them was authentication bypass, to where the communications module, the Ethernet module that you slide into the Modicon PLCs, allows an attacker to basically administer the device for free. You can change and modify user credentials, administrator credentials without authentication. And then here is the proof of concept that we wrote for that. There she is. See, zero-day NICS is very easy. It uses this hidden service API basically to just reset the administrator password, and then you can just log in because that's a set password. All right, last one. Rockwell Automation. RS Links Classic, made by Rockwell Automation, implements Ethernet IP, which encapsulates the Common Industrial Protocol SIP messages. And so basically the SIP messages have this 24-byte header followed by command-specific data. The header lists the command and the length of the command-specific data. However, the application doesn't validate the command data length. So the application doesn't actually check to verify that the data it's processing is as long as it said it would be, which allows us to overflow the stack and control return address. So the vuln was actually in a specific part of RS Links in the connection path parsing function, and it's triggered by an extra long connection path. So you just send it this big packet of data, and the affected function in the engine.dll library parses that connection path to extract a port and stores it into a buffer on the stack. You can specify up to 256 bytes of that connection path, and the buffer starts at about 200 bytes above the return address, so you have control of return. And this POC is in our repository as well. Okay, hopefully that wasn't too bad, right? Now let's look at the fun part. The application of those vulnerabilities. These are all ICS vulnerabilities in attacking our nuclear power plant. Okay, so step one, I'm going to turn you guys all into nuclear physicists in 1 minute. You ready? All right. So nuclear fission is a process where a large nucleus splits into smaller nuclei with the release of energy. So uranium-235 splits into krypton and barium. And when it does that, it releases 3 more neutrons. Each of those neutrons can start another fission reaction. So uranium-235 is the really nice isotope of uranium, and 238 is the naturally occurring one. So when people talk about enriching uranium, they're talking about putting more of the 235 into the fuel. So nuclear fuel is usually about 10% or so, and weapons grade up to like 90% of uranium-235. And remember, those neutrons that are produced, those are key for understanding the reaction and for understanding how the reaction is controlled. So we know that the fission reaction creates heat. Heat is used in these reactors to make water boil and creates steam, and then the steam turns a turbine to make power. So that's it, 1 minute. You guys experts, get it? I don't know why there's even nuclear engineering. You can just Google it. All right, so now let's name the key players inside of the nuclear reactor. Number 1 is the fuel. That's the uranium. It releases the heat. It's the key element of fission. Number 2 is the moderator. This player is the guy that slows down the fission reaction by absorbing those neutrons. Every single neutron that it blocks stops one other fuel nucleus from splitting. Number 3 player is the coolant. So this guy takes heat away from the core, and the heat is the energy. And then the 4th and most important is the control element. Those are like the referees. There's usually 2 of them. And when it starts to get too crazy inside of the reactor, the referee comes in and steps in to stop the reaction. So cadmium, hafnium, boron, all of those elements absorb neutrons. Every single neutron, they absorb them. And so they have the power to completely shut down the fission reaction. Okay, so let's talk about some different reactor designs. I'm going to describe 5 different reactor designs, and each of which is more vulnerable than the last. So first off, and by far the most prevalent, is the pressurized water reactor. There's about 300 of them in the world. And there are more and more of them go into production as time goes on because they're extremely stable. They have negative reactivity coefficients, which means that as the temperature of the elements in the reactor goes up, the fission reactivity goes down. So they're very stable. Boiling water reactors is like the little sister of the pressurized water reactor. They're the same. The only difference is that there's no separate heat exchanger. The heat exchanging all happens inside of the core. So steam is actually produced directly in the core with the fuel elements. And one of the larger BWRs is the Kashiwazaki Kariwa in Japan, which was constructed by Hitachi and General Electric. And this is the control diagram from the NRC for that BWR in Japan. The control systems, all of the instrumentation, all of the safety systems are all on the same network. But don't worry, guys, it's air-gapped. You can see the fully computer-controlled separate response systems. So the redundant safety systems are the emergency core cooling system, and that's on the lower left where it says ECCS. It sprays boric acid into the reactor in order to kill fission. The second one is the SCRAM, which is control rod insertion. That's to the right of the ECCS, and it drops the control rods into the core to stop fission. Okay, fourth one. Canada came up with their own modified design of the pressurized water reactor called the CANDO, and it's a pressurized heavy water reactor. It uses heavy water as a moderator instead of light water. Deuterium, which is a hydrogen isotope. And deuterium already has the extra neutron that light water doesn't have, so it's absorbing less neutrons, which makes it able to sustain the chain reaction more efficiently. And in response, as a result of that, you can use less enriched fuel. So a lot of times they'll use raw uranium or very low enriched uranium to fuel the reactor. So it costs less. But the reduction in fuel cost comes with a safety cost. The fission core is designed with a positive void and fuel coefficients, meaning as steam increases inside of the core, reactivity of the reactor goes up, which results in it's just unstable operation of it. So it creates a situation where fission reaction can run with a disastrous consequence. All right, so for the CANDO, let's talk about some safety systems in there. This is for the pressurized heavy water reactor, the Canadian one. This is the schematic of the Canadian reactor in Darlington. This information is from the US NRC, the Nuclear Regulatory Commission. The Office of Nuclear Regulatory Research publishes all of their research and reference material at nrc.gov. That's where I got that. So the Canadian system relies on computer control through 2 redundant computers that manage information and alarms. They're aware of how unstable the reactor design is, so they implement these safety systems with specific diversification requirements. There's 2 critical safety systems, right? SDS-1 and SDS-2. The absorption rods, which drop into the core, and then the boric acid injection, which injects boron and absorbing all the neutrons and killing fission. So the 2 safety systems are required to use different operating systems. One has to be on Windows, one has to be on Linux. They use different architectures. One has to be with an Intel chip, the other one has to use AMD. They also have to have different software languages. So one of the code, even if the logic is exactly the same, one has to be written in Fortran and the other has to be written in C or something. Even so far as to being developed and coded, they have to be run by separate teams. So if you wrote code for SDS-1, you can't write it for SDS-2. If you operate SDS-1, you can't operate on the second safety system. So the result of this is just that you need a couple more 0 days. But no big deal, guys. You can just borrow some of ours from earlier. All right, last reactor type, the AGR, Advanced Gas Reactor. It's a gas-moderated reactor that's used in the UK, and they looked at the problem of void coefficients inside of the reactor where the coolant can boil, causing an increase in reactivity. Like, what do we do about that? And they just took it out of the equation. So they use gas to cool the reactor. And so you don't need to consider state changes of the coolant, as it doesn't come into play for design considerations. So the very last and best reactor of all is the infamous Russian reactor, the one that was used in Chernobyl. It's extremely unstable because as liquid boils in the core, reactivity increases. And it causes a positive feedback loop. So in general, Russia has been phasing these out. Like they decommission them like crazy. There's only a few of them left. So now our attack scenario. So our network will always be air-gapped as a precaution, so we need to start with an initial infection to get into the adjacent network. And it's easy to do with some phishing or just consumer-grade malware targeting an employee corporate network. Now, once we're into the adjacent network, some human interaction or other propagation zero-day will be required, allowing us to get into the control network. We've seen examples of this before with Stuxnet, as an example, used a Windows vulnerability over USB and a man on the inside to jump the gap. And once you're in the network, running on an operator panel, one of the peripheral systems, the next step is to get onto one of the controllers. To get onto one of the controllers, we can use another vulnerability, for example, the Siemens authentication bypass, to spread to the controller inside of the production network. And that was the first vulnerability that I described here. After the infection phase of the attack is over, we need to start modifying control systems. Modifying PLC logic in production systems can actually be accomplished in a couple different ways. And so one of the recent examples was at Black Hat, the University of Tel Aviv. They discussed some vulnerabilities in the SIMATIC PLCs to do this. Another way is the malware implant could just wrap the communications module on the controller, modifying traffic in and out to do automatic function changes and signals going in and out. And then for our attack on the power plant, we need to be able to stop the coolant pumps from providing coolant to the reactor core. And then we need to also be able to withdraw the control rods to increase the power of the fission reaction beyond criticality. The third and integral part of the attack is delaying response by operators on the plant by providing false telemetry and the illusion of control to the plant operators. So simulated logic can be implanted into the controller to send calculated temperatures, pressure, power readings, all up to the operator interface. So as the plant operator attempts to move control rods to slow the fission reaction, the implant sends back simulated signals to give the operator the illusion that the reactor core is operating under stable conditions. And then the last part of the attack is to disable the critical and redundant manual and automatic safety measures. So those are those safety systems that we looked at in the can-do schematic. And the attacking malware can replace the logic in the emergency core coolant system and in the SCRAM control rod insertion such that they'll not trigger from automatic or operator manual controls. And this allows the core time to heat beyond design limits and start either a meltdown process or some internal steam explosion to where conditions go beyond the design specifications. So the attack scenario, for the Russian RBMK reactors, they're very unstable and still in use in some places in Russia. And they rely entirely on those logical control systems to maintain stability. If an attacker were able to achieve control of safety over control systems, they could easily cause a catastrophic explosion within an hour. It happens really quickly. The pressurized heavy water reactor used in Canada and India, they're more stable than RBMKs, but less stable than the light water reactors used in the US. So because they use unenriched uranium as fuel, their fission reactivity actually increases as the fuel temperature goes up. They'd also allow an attacker to create a condition that would be beyond design spec for the core and a possible runaway fission reaction for the worst case scenario of a core thermal explosion. Now, all power plants in many countries, including the US, don't use those designs, but they'll use these light water reactors, the PWRs and the BWRs. This was the kind of reactor that Fukushima was, for example, and 3 Mile Island was a BWR. So these type of reactors are designed to make it impossible to create any circumstance where there's a runaway fission reaction. But there's always still the case of the core melting down. So an attacker would be able to cause this over a longer period of time by removing coolant flow from the reactor. So as the reactor byproducts decay, they're still adding heat to the reactor core, which eventually, as it keeps heating up, would eventually melt the fuel rods and then would eventually melt the surrounding enclosures. So I just wanted to end the presentation on some final thoughts that, like we're spreading some kind of fear and uncertainty here, but just that nuclear power in general is very good. It's, well, let me say that, in order to pursue an attack vector, I'm pulling out all of the vulnerabilities of a system, looking at the weaknesses. So, it's typical of a technology by this name to evoke fear, because it has nuclear in there. It evokes fear and uncertainty. So it's a very heavily regulated industry because of those reasons. And so it has an increased safety, compared to other power industries. So in the US, also we get more than 20% of our power from nuclear, and there's never really been a bad incident. And on the other hand, one other thing to note is that this type of attack could really be applied to any industry. It doesn't have to be an attack on nuclear. So these SCADA devices and these ICS devices, how easy these vulnerabilities are to find, makes you have to consider more heavily the OT and ICS environments. So that's it. And we have our proof of concept repository on GitHub that has all of those. It has exploits for all those 12 vulnerabilities. And if you have any questions, yes, you can. I'm available on Twitter. And thank you guys for coming.